Hello and welcome back. In this video, we're going to be talking a little bit more about points of inflection, in particular, a special type of point of inflection, okay? All right, and so for this particular one, we're going to be talking about the horizontal point of inflection. Remember, that's where we have a stationary point where our curve changes concavity as well. And it's going to happen on this particular curve here. So I'm going to show you where it occurs. Now, just to sort of jog your memory, all right, this is what our horizontal point of inflection will look like in this particular case. You'll see our gradient is 0, all right? And we go from concave down to concave up, okay? Alrighty, so let's get stuck into the particular question. We're going to follow the exact same steps before. And again, I'll keep the same scaffold so that you can follow it along easily. Remember, the point of inflection occurs when the second derivative is equal to 0, okay? So step 1, we're going to differentiate. All right. Now, this is where it's important for both of your curves, for both of your derivatives to come into play, because we need to check whether or not there's a stationary point. There's a slightly different order to how you can do this. I don't mind what you do. All right. I will talk about why I do it the way I do it here and how you can do it another way. All right. So in this particular case, okay, I'm going to find the first derivative, y dash is equal to, and this is just going to be a chain rule. So we bring the power down. All right, 3 times 2x minus 1, subtract 1 from the power and multiply by the derivative inside. And we end up with 6 outside of x minus 1 all squared. Okay, now let's find the second derivative. Again, it's another application of the chain rule or function of a function rule, depending on who you talk to. All right, bring the power down, multiply by what we had before. Inside the bracket stays the same. We subtract 1 from the power. So instead of 2, it'll be 1. All right, and then we multiply by the derivative inside. So our second derivative is now equal to 12 outside of x minus 1. All right, now what I'm going to do is I'm actually going to find, and I'll put this in purple so you can see that it's slightly different from our last step. I'm actually going to find the stationary point. Okay. All right. Now, why am I doing that? Because I know we're going to get a horizontal point of inflection, but this is also the scaffold that I use when I do curve sketching. So I'm sort of trying to prepare you for a little bit later on in terms of how we do curve sketching. Okay. So we're going to find the stationary point. Now, remember, all right, we let our y dash equal 0. So our first derivative equals 0. All right. To find any stationary points. Okay. So therefore, looking at our first derivative, that's this one here. 6 outside of x minus 1 squared is equal to 0. All right, we're going to divide both sides by 6. So now we have x minus 1 squared is equal to 0. Taking the square root of both sides, well, the square root of 0 is still going to be 0 no matter what. We end up with x minus 1, and then adding 1 to the other side, we have a stationary point at x equals 1. I'm not going to find the coordinate of this. I just want you to lock into your mind the value of x equal 1 being at the first derivative equaling 0, okay? All right, so continuing on with my next step, all right? As per usual, now we're going to find the points of inflection, all right? So find our point of inflection. This is where our concavity changes, and that's actually what the question is after for us to do. All right, so find the point of inflection. Okay, so to do that, a possible point of inflection occurs when our second derivative equals 0. So we're going to let y double dash equal 0 to find our point of inflection. Okay. All right. So looking up at our second derivative, we have 12 outside of x minus 1. X minus 1 is equal to 0. Divide both sides by 12. So x minus 1 equals 0. And then x equals 1 is where we have a possible point of inflection. Now, here's something that I want to point out. Notice that at x equals 1, we have both a possible point of inflection and we also have a stationary point. This is where you start to gear yourself up and get ready for the fact that this point of inflection may be a horizontal point of inflection, okay? Because they are equal to 0 at the same x value, okay? So we know that it's only a possible point of inflection. Our step 4 is that we must test, okay? All right, we must test to check whether or not concavity changes. All right, so step 4, test concavity changes. Okay, so, all right, we draw our little table again. This is called the second derivative test. All right, and we check between x and our second derivative. And we go here. All right, so in this particular case, our value of concern is x equals 1 from down here. All right, from what we found earlier. And we know at that point, our second derivative is equal to 0. So that's our possible point of inflection. And now we just want to test to make sure on this side or on this side that we end up changing concavity as we go across. All right. All right. So I'm going to pick points that are really, really close to 1. I'm going to pick the point of 0 and I'm going to pick the point of 2. It doesn't really matter what points you pick as long as they're close to the point of inflection and they do not go over other stationary points or other points of inflection. Okay. All right. So if we want to check the value of 0, I'll do this in purple so you can see my working out. Subbing it into the second derivative, that's this one just here. All right. 12 times 0 minus 1. 0 minus 1 is negative 1 times 12 is going to be negative 12. So we have negative 12 here. All right. Same thing for when we test 2. All right, 12 times 2 minus 1. That's going to be 2 minus 1 times 12, which is 1 times 12, which is just 12. So have a look at the values that you end up with. All right, when you're checking the concavity changes, you'll notice that we've gone here from a negative to a positive, okay, which is very, very good. I write that just to remind myself. Negative to positive, and I draw a little arrow, okay? Because the concavity changes, it is indeed a horizontal point. It is indeed a point of inflection. All right. So the other thing that we also have to say is because the first derivative is 0 and the second derivative is 0, it is a horizontal point of inflection. So this is how we write that. So we say, therefore, concavity changes. All right. I might actually just sort of fix that up a little bit because we can write it a little bit more concise. All right. So therefore, as y dash equals 0, y double dash equals 0, and concavity changes at x equals 1, there must be a horizontal point of inflection. And that's exactly what we'd expect on a basic cubic curve, all right? Finally, the last little thing that we need to do, all right, part 5 is actually just find the actual coordinate, all right? So find the coordinate. Okay, you don't need to write down these steps as you go along, all right? This is just a scaffold to sort of help you sort of attack any questions that are like this, right? So this is where we let x equal 1. We're going to put it into the original function, right? Because that's where we want to find our y value. So y is equal to, we go up to our original function, all right? Y is equal to 2 times 1 minus 1 all cubed. Inside of this bracket, it's going to become 0, all right? And then 0 cubed is still 0 times 2 will still give you 0. So therefore, our horizontal point of inflection, so horizontal point of inflection at 1, 0. Okay. All right. So that's your basic step-by-step process to show that you have a horizontal point of inflection, which is just like sort of a special type of a point of inflection. It doesn't happen very often when you're doing your working out. So it's always good to check. And that's why I do this purple step over here. I find my stationary points and then I verify once I check over here with the changing of concavity. Okay. All right. So I hope this helped. We've got one more video coming up talking about a special case, which is why you have to check that concavity changes when finding the second derivative equal to 0 for it to actually be a point of inflection. Okay. I hope this helped. Thank you.